looks okay. All right. All right. Allegedly, we're live. Let's see. Need to change that. And now I should be able to see you guys chat if someone says a message at me. But, all right. So I've been waiting for this source code ever since the paper was first mentioned. A few weeks back, I believe, is when Saint first actually came out, because it was this month. That was about 2 weeks ago then, a little less than 2 weeks ago. And the implementation is called Saint. Let me go ahead and throw a link into the chat. And essentially, what's different about Saint is it's kind of everything I've ever wanted out of a tabular implementation, like a modern tabular implementation, if that makes sense. Because you have row-wise attention, contrastive pre-training, and the other thing I like about it is you have the ability to represent your categorical features as continuous variables. And so what that means is we make full use of the embeddings, which, I've worked quite a bit with tabular, and that's something that I tend to look for when it comes to these sort of implementations. And just, things that I'd like to see at least tried with tabular, even if it's maybe not better than, say, XGBoost. I at least want to see, where we're at right now with tabular, because yes, I am biased towards neural networks. Yes, just because it's not the best, though, doesn't mean you shouldn't ignore it. So let's sort of look through this paper, and thankfully they have obviously released a source code. That's why we're doing this in the first place. But let's go through and look at a few of their results, as that's, obviously what we're most interested in. So first, this is just a very high-level overview of their model and the self-supervised pre-training as well as supervised fine-tuning. Rather than look at this, I'm going to sort of show you guys how I approach these problems. And usually, if there's source code, or if there's source code to be released, I wait and then learn from the source code and then attempt to re-implement it in fastai. And so that's what we're going to try and do over however many streams that might take. This is kind of just me doing my thing, and you guys are basically here for the ride and can ask me any questions that you might want. Now, something that's important here is they discuss in, I want to say, this paragraph. Yes. So in this paragraph, they talk about representing the continuous variables as categorical features. So I'll just sort of read what this states. So in language models, all tokens are embedded using the same procedure. However, in the tabular domain, different features can come from distinct distributions, necessitating a heterogeneous embedding approach. Tabular data can contain multiple categorical features which might be used on the same set of tokens. Unless it is known that common tokens possess identical relationships within multiple columns, it is important to embed these columns independently. So essentially what that means is if we have, say, multiple this is a very low level approach, and there's room for interpretation in there. Hey, Dr. HB, nice to see you. But my understanding of this, at least, is at a very low level, we can have no, absolutely not. We just got started. So essentially, what this is stating is we can have multiple Boolean columns as a very basic example. So we have column A that's true false, column B that's true false, column C true false, and each of them have the same tokens. But if column A relates to column B, then that's important. And so that's more or less what it's trying to get at there. So unlike the embeddings of tab transformer, which uses attention to embed only the categorical features, we propose also projecting the continuous features to a d-dimensional space before passing their embeddings through the transformer encoder. And so to this end, we use a separate fully connected layer with a ReLU nonlinearity for each continuous feature, thus projecting the one-dimension input into d-dimension space. With this simple trick alone, we significantly improve the performance of the tab transformer model. So essentially what we do here is, if we just, try and convert this into torch lingo, so they use the tab transformer model, and they project the continuous features, presumably through some embedding layer. We'll have to go look at the code to see just what tab transformer is doing, as I'm actually unfamiliar with tab transformer. It's been a little bit since I've looked at the new tabular stuff. And then they just grab a NN linear layer and then throw a ReLU at the end of it. So that in a nutshell is how they do it. But the interesting thing to me is this is all done through attention. And, attention is all you need. But in a very serious note, attention has been something that I've been very curious about, especially as it comes to tabular data, because it can really help drive certain interpretability aspects like, feature importance and understanding, to a certain degree, how your model is doing. That's a very black box question. I know there's discussion and arguments over it, but it gives us some intrinsical insight into the model that's not left up to interpretation by, does the theory back it? Because in this case, it's attention. That's the very definition of it. Now, they mention intersample attention and the training and fine-tuning. What I'm mostly interested in from here, because we're going to look through the code to see what all they're doing there, is the experiments. So they used 14 binary classification tasks and 2 multi-class classification tasks. Now, let's see what else we have here. Details of these datasets can be found in Appendix B. Let's go take a look. So the 1995 income classification dataset, which, if I had to imagine, might be our adult sample dataset, because I believe that's the census dataset. Let's go look at Kaggle. Income classification. Because if this is, in fact, yes, it is. It is whether or not you make above or below 50K. So obviously it goes by many names: 1995 income dataset, the adult sample dataset, the 50K dataset, the salary dataset. So this is the results that the specific dataset that we're going to hopefully attempt to recreate, if not maybe see if any of the fastai special little bits can make it perform a little better, with the use of different optimizers, maybe a different fit cycle, so on and so forth. And then we have the Arcane dataset, Arrhythmia dataset, bank marketing, credit card. A few of these I don't, auto online shoppers dataset I recognize. So there's a few well-known ones. And then MNIST, which makes perfect sense. So what I'm going to attempt to do with sort of what we're rolling with is we will stick with fastai. And so what I mean by that is we're going to use the income data set initially just to do a baseline in fastai and then maybe, and then B, attempt to get what they've got with the income data set. And then after that, we'll sort of add in the fastai tweaks that we have. And then from there, after seeing how that does, we'll go and throw it on something like the Rossman data set, where it's realistic monthly income based on profits of a company. So that's sort of my game plan towards how I tend to look at these tabular models and what they're working with. And then when it comes to training and stuff, we will just roll with a regular Collab notebook. I'll make it public. Depending on how much customizing we do, I might turn this into some sort of mini one-off library. With NBDev, I might not. If I don't, this will be thrown into the Walk with fastai repo under my live stream stuff. But that is essentially the game plan for how we're going to go about doing this madness. So first, let's sort of peek through their source code. I've already started to look through this. They just made this live like just a little bit ago, and I couldn't help myself. But one thing I do very much so appreciate is it's very approachable and readable. And so what I mean by this is there are a few tabular implementations and other model implementations where they tend to abstract a lot from you, and it's sort of just running a bunch of things in the background. Whereas with the sane implementation, it's very much so just, it is what it is. This is exactly what you would do. So like this is the train, which obviously you have, all your arguments, and then resetting your arguments. But the training loop, like building the data set, building your model and training are all extremely straightforward, which I very much so appreciate, because like this is a very, very standard, simple PyTorch training loop minus all of the contrastive stuff when it comes to that. So we're going to try and recreate what they did as best as we can by bouncing back and forth through the source code and through just what we know. So first things first is we're going to go ahead and open up a notebook. Now, for the time being, I'm going to throw this into a Scratchpad. Yes, I'm glad that you saw that. It's even more than cut mix. There is cut mix, there is mix up, like the tricks that they have with training this tabular model is just extremely impressive, because you have, essentially everything you would want. You have the contrastive pre-training, mix up, and cut mix. I mean, that's from like a fastai perspective and things that I look at, with vision, that's the basic nitty gritty when you want to do either just self-supervised or just training in general. So the fact that you can use potentially both, from what I'm understanding here, or even just one in general, is absolutely fantastic. And so part of what I want to do with this is re-implement this ourselves and just see what we can do. But from there, let's see. Let's go look at a few things. Actually, first, let's look at what they're doing for how should we go about this first? Do we poke into what they're doing there, or do we just start coding? I kind of want to see what they're doing for cut mix. Let's go look at this function. See, like, that's the other thing I like about, like, what they're doing. It's all super small, straightforward functions. X categorical, X continuous, and your noise parameters. So if cut mix, and you also find out little things like this, such as the fact that they're implementing Gaussian noise, or Gaussian noise eventually. So that will be very cool to keep an eye on. But, I mean, this stuff is surprisingly very straightforward to read just from like a PyTorch code compared to other things that I've known and looked at. So let's go ahead and get started. So we're going to go into here, and ideally that's, I opened copy drive. I don't want to do that. Go ahead and open up a GPU instance. And we'll do, well, I guess we don't necessarily need a GPU instance yet. Let's first just make sure we get everything going. So we'll do, we'll go ahead and install fastai and let that run in the background. And in the meantime, let's go to one of my favorite bookmarks, the app examples notebook. Go ahead and throw that in chat. But essentially, I use this notebook anytime I want to test something quickly. So like here, you know, I want to very quickly just, and these are for all of the very basic fastai applications. So like you have the pets data set where it's like the book. So it's got whether or not it's a dog or a cat. You've got segmentation, boilerplate code. You've got text classification, tabular, collaborative filtering, key points. And really what this helps is whenever you're in a situation like this where you just want to throw some application at a model and just get it working before you go and use it on something where you do have to worry about the data set and it's a bit more complex. Here it's just very quick copy paste and you're on your way. So we'll do from fastai.tabular.all import star, our usual tabular bits. And then we'll go ahead and download the salary dataset and build our data loaders. Now, one thing we'll probably wind up coming into issue with here is when we get a batch of data, from a fastai tabular data loader, this just gets a batch. We get the categorical, continuous, and the Y. So I imagine we're probably going to have to modify and change a few things. But the first thing I want to do when we go about this is go ahead and grab and more or less copy what we can from the model. So we're going to do this by just cloning the repo into Collab. We're going to take the easy way out for the time being, just get something working, and then after we have something working, I'll look towards, you know, building out a more custom implementation that's geared towards fastai. So, like, what I mean by this is we're not going to do like tabular learner and passing our data loaders and working everything with that. We're going to be using fastai's base loader, passing in our data loaders ourselves, as well as the model. So we're going the, what I would consider low-level training API, and then we'll build some stepping stones off of that. All right, so let's go ahead and clone this, because the other part of it is we're essentially going to be implementing 4 things. We're going to be looking at bringing in their model. We're going to look into converting their mix-up and their cut mix into fastai callbacks. And then we're also going to look into the self-supervised learning implementation. So I imagine those first 3 we can probably get done tonight, if not bare minimum the first 2. The last one will probably take us the most just because it is self-supervised learning, and there's a bit more that tends to go into play with this. And honestly, I'll probably have to talk to Karim about that, or Karim about that, because his self-supervised library is fantastic, and I'm probably going to take some inspiration whenever it comes to implementing it in a more fastai process. So next thing I'm going to do is just cd into the saint directory, because I believe that, actually, I guess we don't have to. That's very convenient, because now all I can do is just like from saint.train, I believe, import, let's see if this works. From saint.models, and do we have, we do, import star. Let's see if this works. Nope. Okay, so we do have to cd. That's fine. Thought we could get away with it, but apparently not. All right, so now if we do from models import star, looks like we need to install inops. Which I would have seen if I looked at the requirements while we were on stream, but of course I did not. But that's fine. We'll just go with it. Also, please do feel free to ask me questions along the way. If you want me to just like pick apart any of their code, look at what's going on with it. Most of what I want to do though, because we're at a point where essentially we've got the data loaders built, right? We're isolating chunk by chunk what we want to look at. And so this first part that we're going to look at is just the model. So we just want to look at the model and build the model. So let's see how they build the model here. I want to specifically go down to, we won't necessarily worry about that yet. All right, so we have if, all right, so let's look first at how they're deciding this. So the dataset by default is the income dataset. So as a result, we can assume that we can use just all of their default values. Now, what I'm going to do here is just copy and paste all of this. And how do we want to make that readable? I think I see a way. So whenever I want to just like get rid of chunks of code like this and I just want it to be readable for me, I tend to throw up Sublime Text. You can use any text editor you want and just essentially throw it in there. I just copy pasted. I find Sublime easy for me to use just for stuff like this because I don't use Sublime for anything else. So it just works for me. So what we're going to do is find parser add arg and just replace it with nothing. And then I want to do another find and replace. This one will be regex based. And what we want is to replace, how do we want to do this? We'll replace comma type star with the, how do we want to do that? Probably with a comma. And then we'll do one more find and replace query. And let me make sure that I have that up. And we'll go through and do default with default equals, essentially I'm just converting this to a dictionary. Actually, that's how that works. I'm trying to think. So if I have a dictionary A2. Okay, yeah. So we'll replace that with that, and I think that should get us what we want. Dataset, That works. And then our last find and replace is with, actually, we might need one. What I have to do is, boom, boom. Make sure that all of this looks fine. So action store true means it defaults to false. There's a few things we need to just clean up here. Which, yeah, there was a programmable way that I could have done that, but it's only two things. Now we'll say config equals that. And let's go ahead and clean that up a little more. Last thing we'll do is find replace that with nothing. And there we go. All right, so we have the default values, which, as we saw, the default works with the adult sample data set. So now we have our config stored. And just to make, yeah, I guess that works. All right, so now that we have the config stored, let's look at how they build the model. So we set the seed if opt attention is in call row. So I'm going to go ahead and open both of these up. That way we can see, you know, on the left what it's up to and on the right what we want to do. All right, so if we want to do, all right, so let's look at config attention type. So we have call row. All right. Now if we do config ff dropout. All right, so we are going to be overriding some new values. So let's think of how we can do this in a verbose state. So we'll do def change config field val. And we'll do config field equals val. Mostly what I'm interested in is getting the defaults. So print star initial field configuration val new field configuration. This way we can sort of see just how they're changing it and what they're up to. We'll do return config. And now let's go through and change the configs. So we'll do config equals config, or change. No, I don't want it. Actually, I want this to be change config. There we go. All right, so we'll do config. The first field is ff dropout. And then we're passing in 0.8. Now let's just do this for the rest of it in here. 1, 2. All right, so it looks like here we just have 2 because we look at ff dropout and the transformer depth, and then if the data set is in one of these, we do something, but we do not have that. Go ahead and pull that back up. So we have transformer depth, and this is set to 1. All right, so we had initially 0.8, which I think is what I changed. And let's go look. No, okay, so these are the defaults, but that's fine. At least now we know if something changes, we can log that. All right, we don't care about any of those, so the rest of the defaults are fine. We won't work with weights and biases yet, so let's look at the mask params. We'll do mask prob. Also, for why I'm manually retyping this part rather than copy paste, for me, I tend to remember and think about things when I actually physically type them rather than when I just copy paste. And so even though, yeah, it is a little dictionary, it makes me think about what we're doing. So here we want to set this to config. So we want the train mask prob. So let's go see what that is. So our train mask prob is currently 0. And then we have avail train y, which is set to 0. And then we have test mask, which I imagine will also be set to 0. It is, because it's, sorry. Oh, interesting. I imagine in this case, we're saying that the test mask is the validation set, so I can understand why we're doing this. So we'll do train mask prob. And then we have the, I imagine, PyTorch mask parameters. So this is config mask prob, which is also 0. So we'll do pt mask params, mask prob of 0, avail train y, also 0, and then a test mask of 0. All right, so now we have some dataset prep. This is very interesting. So let's go take a look at what we're doing here, because I don't think the fastai bit is what we wanted to do. All right, so fill in A, train valid test, cat columns, label encoding. You just fill in A with very, very likely. Loan data. All right, so here, if data set is in data prep auto ML. Interesting. So they use auto ML to prepare and work with the data set. Well, we want to recreate what they did. So as a result, we're going to use the data set they did. Let's go through and go ahead and bring... Oh, I want to bring you back into there. Thank you. Let's go ahead and grab that data. So we'll do URL and then path untar data URL dest equals adult. Now fastai should automatically, yep, here we go. So here's our data set. So for those that weren't aware, fastai's untar data goes and grabs a usually gzipped file, but it also works with regular zip files. So that's, and it goes through, pulls it, and then extracts it where it wants to. So here we went and grabbed the AutoML data set and just threw it in here. All right, so what do we do next? Next, we make the directory and download it. That's fine. All right, so now remember, I did say this was going to be similar to how I do things. So you will see a decent chunk of madness going on. All right, so we have path. So we have P1 equals... Now they use OS keyword and do a bunch of stuff like that. I'm just going to do F strings and wrap it around a path. Actually, we don't even have to do that. So we can just do path slash... Sorry if you heard something. That is my cat. Who has now left the room. All right, so I believe just do path ls. Interesting. All right, let's do path equals path. Oh no. Oh, we don't? Interesting. Okay. Yeah, mostly what I'm also nice to see you in here. That's very terrifying. hopefully I don't butcher any of your code or the magic you have put into this paper. But essentially what I'm trying to do here is recreate what you guys have done with your stuff in fastai. Okay. And just sort of see what we can do from there. So we don't, let me go back and reread this. So we don't need the adult sample, the adult data set to run the code. It was left over from older code. Oh, okay. All right. I understand what you mean here. I was mostly worried about if there was something special with the data prep you had done, but looking at it here, I don't think so. So, all right, that makes me feel a little better. All right, so we're just gonna use the fastai dataset then and just roll with that since we've already got it prepped. All right, so we'll go ahead and clean that up a bit. All right, so prep AutoML, NA, targets, features, category binary, labeling code. All right, now this is where things get a little interesting. Mask detect is none. Let's go look at this. Data prep, and here we have data prep, mask params. Op data set, offset seed. Now, I think in our case, the mask detect was 0 in here because all of our mask params were set to 0. So we're going to ignore this for right now, but we'll look at that a little later. All right, so NP zeros, train features. All right, so I'm just looking at how these masks were made. So we have temp, target. I think I might have missed something. So for call, train. Okay, interesting. So we're just literally making a mask of all of our X's, if I'm understanding this right. And then we also make a masks or NP multiply. Yeah. Just an empty mask with this one like of all of our X's and all of our Y's. Interesting. Okay. That should be more than doable enough. So if we do dataset.x's, so that actually should be really easy for us to do. So if we do mask np1s like dls.train.dataset.x's.values. Let's see if this winds up working. If it doesn't, then, oh, wait, it might. It did. All right, so for those that are wondering what I just did, dls.train is the training data loader. Then I can do dataset, and it gets me this, this essentially tabular pandas, and then I can grab my X's, and then we can grab the values of them. Masks are used just to run missing data experiments, not really relevant to the model. Ah, okay. Good to know. So here, not necessarily relevant to us. We might try and play around with a situation where that might wind up being necessary, and we might try and recreate that one for one there. So, all right, in that case, we can go through and skip that part. Let's go through and make sure that we keep any of the params. So we have, if it's not in there, y dim equals 2. And then let's go ahead and just quickly grab the mean and ST and the standard deviation of our stuff. We should be able to do normalize, right? Yeah, there we go. Means. That's what we want. Dot means. And then we want standard deviations. So Dr. HB asks, so you only need them when there is NaN values, which that sounds right, and it look if I'm understanding this right too, yeah. The model needs the number of categorical dims and indices of the categorical and continuous features. That makes sense. So essentially you're just trying to grab what those indices were. That's more or less what we were doing over there. That makes sense. With how fast AI sets this up, this actually should be really, really easy because we just need the regular length of our what should we need for that? We should just be able to use what fastai has stored for it for a few of that. So and then I'll ping back with what's going on in the chat as more interesting things come up and questions are answered. So we don't need to calculate the attention for those values like for the language models is Dr. HB's understanding of this implementation. Also, we need to normalize continuous data. Yes. So one thing you might have missed is since we're using fastai, this is all of that pre-processing done in like 5 lines of code. So we fill missing variables, we convert everything to categories, and we normalize all our data. So everything is done for us data-wise. So now most of what I'm trying to look at is just playing around with the model and seeing how all that behaves. So let's go through, and I don't think... we use special embeddings for them. Okay. Yeah, that makes sense. Yes, that's part of what made me interested in the paper is the fact that you use special embeddings for the continuous variables. So very interested to see how that winds up doing. So I believe this is set to false for this run. Yep, so we can skip over that. And we can work just based off of what we have here. So let me go ahead and just barely move that over to the side for us. That way we can see it a little more. My cat is yelling to come back into the room now. Yeah, hello to you too. All right. So when they calculated the cat dims, so I'm trying to think of how we can convert this into fastai bits. So let me see how these cat dims are actually calculated. Let's not skip over that. So yes, it's so hard for them to pick a room. So where do we have that? So if we go to data prep, which I guess that wasn't the right one that I wanted to look at. Features. When do we define the cat dims? Categorical dim, and we get categorical dim via... Okay, all right, that makes more sense. All right, so we might wind up doing this slightly differently with just how fastai does a few things. Potentially, and I'll explain why. Fastai tends to also use the NA column as a categorical feature, and I'm not 100% sure if label encoder picks up on that with like just how the order of like fill in A is going and everything. It could though, which if it does, then awesome, we're doing things right. So this should mean that all we need to do is train categorize. I used to know how to do this. It's been a few months since I've looked at the tabular stuff, but there is a way for us to categorify. Maybe it's categorify, not. There we go. Classes. All right, so here's our categorical dims. So all we need to do here is just say categorical dims equals O length O for, well, I guess in reality it would be OI for OI in enumerate dls.train.categorify.classes.items. So what is essentially happening here is when fastai preprocessed the data, it went and checked what all of the unique values were in every column. And then since also you can have, not available or a missing categorical column, we also have an NA tag. And so all we're doing here is essentially setting up a similar dictionary to what they have here with the length of the categorical dimensions in every one. And it seems I missed a syntax error. There we go. So now if we look at categorical dims, each of these, what did I do here? Oh, I know what I did here. So we have we'll do OI underscore. That's better. Forgot that enumerate passes an index, even though that's kind of the whole point of enumerate. All right. So that should be all we need to do from that angle then, because we have our cat dims and our cont indexes. I know how to get them, and we'll look into how to do that in a little bit. Otherwise, so we have another param. So we have y dim equals 2. And then we already grabbed our means and standard deviation. Thank you. I much appreciate your contribution to this stream, Max. Ready to go back out of the room? And there he goes. All right, so let's see where we're at to now. So now we're at config SSL avail y, which is not greater than 2, so we can, or greater than 0, so we can skip that part. Train batch size equals config, well, we'll just name everything the same, so we'll do train batch size equals op, which would be, in our case, config batch size. All right, 256, reasonable enough. We already have our data loaders built, so we don't have to worry about this step. If op data set is not mnest, all right, so we have. Thank you very much for joining us. It was nice to have you on here. I will definitely ping you if any of us have any more questions. But we are absolutely thankful that you decided to pop down in the stream for us. And then Dr. HB said, I think I found that if for continuous MLP, hidden mults are 4 and 2. Okay, awesome. One thing I don't think you were here for, Dr. HB, was they based their this attention on the tabular transformer. So I wasn't sure, I'm not sure if you're aware of that one, but transformers are what's working in the background for the masks. which I found very interesting. I was not aware that there was a literal tabular transformer. That was very much so news to me. All right, but in any case, back to doing the actual important stuff. All right, so let's recreate what they did here. So we'll do cat dims. Ooh, cat continuous variable. Continuous variables are embedded through the embed data mask function. I kind of want to take a peek. And let's see if we can't find where that might be. Here, Dr. HB, you go ahead, and if you want to go and find some research on where all that is, let me know where that's located at, and we'll go through and take a peek at that if I don't get to it first. All right, so back to this. Cat dims, np append, np array. Actually, need an equal sign. Append, np array, cat dims, np array, which I imagine this is for our imagine that 2 comes from the fact that the adult sample is the only data set not here, and that's our continuous. It's what I imagine, at least. So I messed up here somehow. Dot values. I think that's what we want. Categorical dims. Dot values. Int argument string embed data mask. Okay, awesome. What did I miss here? Do that. For some reason, it's blanking me on how to turn this into something that a numpy array can expect. See what we can do from this. Absolutely nothing. All right, well, we'll just do it by hand. Not the end of the world. For this small of a task, and then we can worry about that later when we get into something like Rossmann. 17, 8, 16, 7, 6, 3. All right, so now we have our cat dims. Now let's build the model. All right, so we have saint categories equals tuple cat dims num continuous content IDX is, I'm assuming in this case it's just 2. But in reality, it might actually be more than that, because we can do length dls.cont names. Yeah, because here we have, we don't have any missing, so that works actually. Dim equals config embedding size, and let's go take a peek at what that is. All right, so that's 32. Dim out equals 1. Depth equals config transformer depth. Heads equals config attention heads. Dropout. Then we have FF dropout. Ah, yes, there's those MLP hidden mults, literally right here. MLP hidden mults equals 4, 2. Continuous mean STD. That's interesting. So we're just gonna hope that this winds up working how I hope it will. That doesn't necessarily mean it will. So it seems like they project the continuous to a 32-dimensional MLP layer. All right, once we actually build the model, we'll go through and look through the model code. We can go look at what all that's doing. And hope that I've set that up right. Cont embeddings equals config cont embeddings. Do we actually have cont embeddings key? Oh, MLP. Okay, there we go. Yeah. So that's the embedding type, I imagine. Attention type, config attention type. And what do we have going on for here? Call row, awesome. There were, I believe, 3 that they mentioned. It was call row and just call in row, if I remember correctly. Final MLP style, config final MLP style. So they normalize the data inside the model. No, it was, I think it was done in the pre-processing. Let me go back and look here. Maybe it was. Norm. Wow. Okay. Actually, now you've got me curious. Oh, no, here it is. They do it whenever you initialize the data set. That's where it's done. So this is that so then why do you need mean standard deviation? Yeah, that's actually a fair point. Okay, now you have me curious. Let's go take let's I'm skipping ahead of where I wanted to look, but I want to see. All right, so we have model. Row call transformer, MLP, tab attention. Which also, I'm going to wind up rewriting this myself as well. Mostly due to style choices and some of the fastai things that we can do with it. And then I think we do pre-trained model. All right, Saint. All right, so let's see here, because, oh, no, you're fine. Multiplication, number continuous, tension dropout, scaling. I don't think we wind up needing it, because I don't, oh, yeah, continuous mean and STD. Okay, let's go see what we do with this. Lovely. Thank you, Kat. Much appreciated. So we don't actually do anything with this. Looks like we just pass it in. So that might be some leftover code, unless it's for here, maybe? No. Yep. Mean STG. Yeah, it looks to be a bit empty. So not quite sure what that is. We can probably go ping one of the authors. I'm avoiding the name mostly because I know I'm gonna butcher it. Galfami, I hope. I'm sorry if that's wrong. I'm terrible at pronouncing names. But it looks like it's some unused code. I'll ping them and see what's up with that, and if there's something about the I'm gonna go write that down in a note real quick just so I remember. All right. In any case, we pass it in. Good to know we can't pass that in wrong. Final MP style, which let's go take a look at what that is. Let's go look at that winds up being, just so we can understand a little bit more about how this architecture works. SEP, interesting. I'm loading all the configs now, so once we go look at the model, we can actually understand how everything is working. And then here our YDIM was 1. So hypothetically, this should give me no errors. Wow, that is the most painless model initiation I've ever seen when it comes to stuff like this. Usually I wind up doing it wrong. So now if we go and explore the actual model, let's go and... Actually, what I want to do for this is... I want to try and use some fastai fancy stuff. Key being try. Callback. Hook. I just got to find the one that I want. So I think it's module summary. All right, so layer info learn. All right, so let's see if this works. Learn equals learner DLS model. Hypothetically, if nothing kills me, okay, so there is some special stuff about how things get in. Oh, I see why that's special. All right, so we're gonna have to do some special stuff with callbacks, from what I can see. Potentially. All right, well, that's mildly disappointing. I was hoping that we could just use that, but that's fine. We can just look at the raw model instead. All right, so, and not disappointing from a them perspective, disappointing in I have to do more work, but that's okay. Usually that's how this goes. This is more smooth than any of the other stuff I've been trying to do so far when it comes to implementing and doing these papers. Also, probably go for another, I don't know, 30 minutes or so, see how far we get. Because we've already been live for what? How long? 8:30? Yeah. Well, we'll go for another 30, 45 minutes and then see from there. And you want to come back into the room? Little nightmare. All right. Yeah, go over there. Okay, so this is the MLP attention module. So this is that send it through a linear layer, take the ReLU activation, and then project it down to a 32, to an out dimension of 32 in this case. And then here's the row call transformer that they wind up using, which this is, this should be the original transformer. This shouldn't be what they did, if I understood the paper right and what's going on here. They just built on top of that. Layer norm, the attention module. GE, okay, so they use glue here. All right. And then we have our masked embeds. This is still a little bit in the arch. The MLP module, our actual embeds. And I imagine after we get all the way down through this, somewhere it should give mini SE. Oh, where did you see that? Very cool. Oh, this right here, potentially, I think. Oh, no, that's what this is. Yes. This is a mini self-attention block. Yeah, for the continuous variables. Yes, that's what that whole is, which it's a, regardless, it's a very interesting architecture. Regardless of what winds up happening in this madness. All right, so we have the model. We have the data. Next, we need to attempt to train it. So we'll work on that for the next, you know, 15, 30 minutes, see how far we get, and go from there. Now, part of what we're going to do here is, and why I wanted to record this rather than just work on it myself, is this has actually kind of been this is what I wanted to be a lesson in the new course that will come eventually. Um, it's not going to be this semester, just with how school is going, but I wanted to do a lesson like this where we just take some paper and we go through, how do you debug things? How do you implement it? Yes, forward pass. Um, and so I kind of wanted to just roll through all of it. So let's, so part of that was, taking what we have here, this raw torch training loop, and bringing it over to fastai one step at a time. So let's see how their training loop looks, which actually is, despite all the extra stuff, a very, very simple training loop. There's not a whole lot going on here when you get down to the nitty gritty. Because essentially, all right, so we start the model on train for every data loader. Xcat, xcont, cat mask, con mask. I think we might have missed a step in generating the categorical and continuous masks. So good to know we got to go back for that. Now, the cut mix and the mix up stuff, that I do want to implement as callbacks for us. I know other libraries like to do mix up as just a regular data augmentation function. This is actually an instance where it's a little bit better that we have fastai for this, because what we can wind up doing is just make it into a callback and use the callback rather than having to worry about adding augmentation to the data loader, and completely break how fastai tabular works. So let me prepare the features, and then image feature if, all right, so this is if we're doing self-supervised. Oh, this is interesting. We're gonna explore the contrastive stuff later, because it just looks very, very cool. Oh, also, that's a little important. So if we're doing any self-supervised pre-training, no wonder why that's looking there. There we go. Yeah, very helpful print message. Training begins now. All right, so xcat, xcont, same thing here. Embed data mask, mask transformer, y reps, y out. Now, one thing that you're probably thinking about here is how that doesn't necessarily look like something we can do in fastai. We're going to write a very, 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 very small callback to make that work. And then that's literally it. Wow. Okay. Because the rest of this is just weights and biases and metric stuff. So very, very small training loop. I like the simplicity. I really like the simplicity that these guys have done here for us. It's so helpful to work with. All right, so let's go through and I want to go look at how these masks are being built. Now, we might have already done this. Ah. Wasn't sure if I was going to sneeze or not. Yes, it is a very cute training loop. I love it. It's so small and so simple. So what we did wrong here is I got to here and then called it a day. Um, we still need to do this part. So let's go see what this does. All right, so actually what I want to do here is data mask split. Where do we see the data mask split? This is fine for us right now because if I recall correctly, all of our masks were 0 because we did generate them. We did 100% generate them. It's all these NP ones like. So that should be all of that. Which as a result, we should just be able to use zeros for that. So we can kind of cheat the code a little bit here. That's fine. That wasn't what I wanted. I wanted our Collab instance. Yes, if I'm correct here, mask.shape, and dls.cats. Oh, okay, that actually does go over everything. That's... Why does that go over everything? This is why it's good to have everything right here. How does our get item look? Alright, so X has X. One has categorical, X2 has continuous. Do you like something special past to... Yeah, so am I. I am very confused with masks, and I work with language models for a living. So I need to look into that. Now, for those that want to, Sylvan is doing a new course here with Hugging Face that goes live literally next week. It's free, and I think all the videos are already recorded, so I'm definitely going to be watching that. All right, let's go and actually look at the model because I want to see how their forward function looks, just to make sure that I'm understanding something and I'm not missing a param. Okay, that makes me even more curious. Why did that fail on us? Because that's exactly how fastai is set up with this sort of model. Well, let's just try throwing a batch at it. This is the other thing I should have done. Whenever I play with a new model, I always grab a batch of data and just throw it at the model. So we should already have cat const y. Yeah, we'll do with torch. No grad. Yes. Seeing Sylvan on camera will be absolutely wonderful. It has been quite a while since we've seen or heard anything from him, since, you know, he stepped away from the fastai community to go do Hugging Face things, but I'm pretty sure Jeremy wants to bring in Accelerate to some degree with fastai v3, so maybe some collaboration could be done. Maybe, we can hope. Alright, so then we'll do model.eval. Everybody call them all, yeah. Model.CUDA. We'll do out equals model. Yes. Okay, yeah. All right, so That's interesting that they have it do this, but that's fine. Yeah, you mean the embed data mask? Let's go look at what embed data mask does. Very good call. Oh, that's gonna be. How do you want to? Yeah, we're probably gonna have to rewrite the model's forward function then to make that work. Because for fastai to really work, if we want stuff like this, well, ideally when you're using the fastai library, that's how you want to do that. In our case, oh no, we're not even gonna rewrite their forward. We can, yes. Um, I'm gonna write a callback that just does exactly what they do here. Because fun fact, if you ever have an issue with how fast AI passes things to the model, you can override that. And so we're actually going to use their code for training. But we're going to pass in. All right, so smart call with that though. So we're going to embed. Where is this? Where does that come from? From augmentation, import embed data mask. Let me guess, it's augmentations. Yep, that figures. I'm too used to fastai with everything storing in aug or single phrased. All right, so we have embed data mask. So we just want to play with something. We'll do embed data mask. So can. All right, so here's how we're going to do this. Dot shape. Cat mask. All right, so I'm gonna copy this over for us to look at. And I think for us to do this, all we do is encoder. So we're just gonna copy this and paste it here, but we're gonna modify it. So X category should be cat. X cont should be cont. Cat mask. I think it's just a blank 64 by 7 of ones. If I'm understanding this correctly, because we have our mask, which is just a bunch of np.like ones. So I think we can do something like this. Mask equals np.ones like cat font mask equals np.ones like. I could be 100% wrong here. And if it is, then that's fine. We can work through it. But I think we can just roll with that since they're all just a bunch of ones and we don't care about the values of those masks yet. So cat con, cat mask, cont mask, model, vision data set should be false. Runs without issues. Alright, welcome to the debugging portion. Alright, wow, that's not very far at all into that. That's good to know. Alright, so we have xcad plus... Let's see what that is. Model.categories offset. What's the length of our DLS.cats? Did I pass a config to the model wrong? Cat dims. 1, 2, 3, 4, 5, 6, 7. Now, that should be right. OO is after its embedding shape. Let's go. Let's go re-pull up the function. No, it's before. Cat data's last column should be Y. Interesting. So you're passing in the Y to the categorical data set? Is that what you mean? Cat data's last column should be Y. So like in this instance, we have cat, right? But we should also smack on this Y to the cat data set. Or to the cat. Okay. I think that should work. Yep. That would be how our magical one column gets in. So we'll go ahead and do... Just keep them a little separated. Understand why we got there. We'll go ahead and do that. Okay. Awesome. Thank you. Appreciate it. What did we do wrong here? Model cat must be of type cat mask. Oh, but we mask it. Treat it like a missing value. Okay. Oh, that makes sense. Okay. I know what's wrong here. I need to cast them as tensors. Cat mask equals tensor cat mask. Mask equals tensor con mask. All right, now it should not yell at us. I lied. All right, so where are we stemming from here? This is something different. All right, so we got a little further. Cat mask. I think I did the same thing with the cat mask. Okay, that's all that's wrong here. Yeah, so I just did the same issue that we did there. Okay, that's fine. So we should be able to do another torch dot ones like, and we do Y. Wrap that down as a tensor, and we'll say Y mask equals that. Just separate it out. And then we can pass that into here. Torch.cat. Cat mask. Y mask. Oh, love me. Oh, no, your code is perfectly fine. This is just me trying to break things and working with it myself. Your code is actually like super, super easy for us to follow. Dr. HB even pointed out that like your fit here is extremely straightforward and clean to read and super small, and I love all of it. You did a great job. Um, yeah, this code is it's clean-ish right now, but even for me, this thing's pretty gross just from my perspective of what I've been playing with. So it's totally fine. Um, I think I actually see what might be wrong here. Yeah, that doesn't look like that should be what it is. That explains that. Is there a ones like that you can pass in a shape for? I guess we can do p.empty 64.8. Yeah, okay, that gets the job done. All right, so let's fix that code. That's a minor little bug. And probably now it will work better. So we can get rid of that. Where did we go wrong here? I mean, we know obviously why we went wrong here, but actually, is this not needed? Make it 0? Okay. Um, Interesting. Okay, I definitely think I missed that one. So if we do that, I think that should make it all 0. Yep. Okay. Cool. Thank you. We would have missed that one. Yeah, that makes perfect sense. So the embedding layers can miss the zeros and just kind of do nothing. Interesting. Expected tensor to have the following. So when it talks about the embedding layers and relation to that mask, it apparently it treats it like a missing value, and so it will try and learn said missing value. That's why we pass in zeros, which that's very interesting. The real question is convert which to int? Mask to int. Ah. Dr. HB, let's not talk about what just happened there. No one saw anything. I did that beautifully the first time. Nothing happened. Okay, so now we have our X categ encoder. I'm actually just curious about the shapes of these. That is not the right variable. Okay. So there's those 32 long representations. All right, so now we're on to the next step. So we just ran the embed data mask, and now we can pass it through model transformer. So here, I think I probably wanted to do something like this. Mostly just because it's A, a little faster, and B, helps me remember that we're kind of just dummy testing things. All right, let me make sure that all of this code is somewhat readable for us. We'll do something like this to keep it all on the screen. Yep, we did that. So that's this right here. So cat mask, last column is all 0. All right, and then we do representations, transformer, and what all does transformer get? Our xcateg encoder and our xcont encoder. Awesome, that ran without problems. The rest should be fine. Reps. Cat dims. -1. Ah. Okay, so now we're working. This is that learning the Y representations. Interesting. Okay. And then Y outs model.mlp for Y representations. Okay, fascinating. That's really cool. I'll write a note about that. Train embeds for awesome. Okay, so we can successfully predict from the model. That is 99% of the headache when it comes to stuff like this and fastai and bringing stuff over. Because now all we have to do is just wrap it in the framework and train and we're done. So, however, I'm getting extraneously tired. So here's what we're going to do. I won't necessarily say we'll do this tomorrow. I want to try to. I got to see how much time I have available. But I do want to finish this up. Because we're literally almost there to the initial stages. We pass something to the model. It actually gets us something back, and we've worked through most of the hard bugs. Everything else should be perfectly fine. So I'll go ahead and push this to GitHub for folks to look at. I'll probably make a new repository, just Saint Experiments, and I'll post about it on Twitter. So if you want to find it, just go ahead and search Twitter thread. I'll also post about it in that announcement tweet for the live stream. But thank you so much for dropping by, and it's amazing to have one of the authors for the paper just go and poke her head in. It's an absolute pleasure to have you on the stream, and it's been really appreciative to have you debug and help us along the way. It's awesome. Thank you for doing that. And thank you guys for coming along and working with me on this. Hopefully, within the next few days, we can get it fully working in the with fastai. So thank you so much, guys.